How do you balance accuracy and efficiency in CFD software? Imagine trying to get a clear picture of how air flows over a car while also wanting to finish the analysis quickly. That's the challenge engineers face when working with computational fluid dynamics software. It's all about finding the sweet spot between getting precise results and saving time and resources. First, it's important to understand that making a simulation more accurate usually means using a finer mesh. This means dividing the model into many tiny cells, which takes more time and computing power. Using complex turbulence models or detailed physics also adds to the computational load. On the other hand, simplifying the model by using coarser meshes or basic physics speeds things up but might miss some important details. One way to strike a balance is by choosing the right modeling techniques. For example, if you're analyzing a rotating machine like a pump, you might use a simplified approach called the multiple reference frame method. This method avoids the need to rebuild the mesh every time step, saving time. But it might not capture all the transient effects perfectly. For more detailed flow analysis, combining this with fluid structure interaction models can give better results without taking forever. Mesh optimization is another key step. Adaptive meshing tools can refine the mesh only where it's needed most, like near walls or sharp interfaces. This way, you get better accuracy in critical areas without creating an overly large number of cells everywhere. It's about focusing your computational effort where it counts. Choosing the right numerical schemes also helps. Some solvers are designed to reach stable solutions faster by using fewer iterations. High-performance solvers that work well with multiple processors can cut down simulation times significantly. This is especially helpful when working on large models or complex physics. Selecting turbulence models wisely is important too. For quick, rough estimates, simpler models like the K-epsilon are often enough. But if you need detailed turbulence information, more advanced models like large eddy simulation provide that, though they requiring more computational power. Only include physics like heat transfer or radiation if they truly influence your results. Adding unnecessary physics can slow down your simulation without adding value. Utilizing powerful computational resources can make a big difference. Cloud computing or high-performance clusters let you run larger models faster. Workflow tools that streamline setup and post-processing also save time and reduce errors, making your entire process more efficient. When working on early design concepts, it's best to use approximate models to quickly explore many options. Once you narrow down the best design, you can run more detailed, accurate simulations to confirm performance. This approach saves time and resources throughout the project. In real-world engineering tasks like designing turbines or cooling systems, balancing accuracy and efficiency helps you get reliable results fast. It allows engineers to improve designs rapidly, reducing the need for physical prototypes and cutting costs. In the end, finding the right balance depends on your specific goals, available hardware, and the complexity of the physics involved. Combining smart modeling choices, mesh strategies, solver selections, and computational power lets you produce trustworthy results within a practical timeframe. That way, you can make better decisions and move your projects forward smoothly.